Primary 6 from Jipa Primary School. For this lesson, we'll be recapping on what we have learned and proven for the last lesson. So we'll be continuing on with the physical chemistry for hydrogen spectrum series. So for this, over here we see the Rydberg's empirical formula. Before we continue, I need to mention a few things. So first, 1 over lambda. 1 over lambda, what does it represent? Well, 1 over lambda represents the wave number. So now I know 1 over lambda, but what is lambda? What does lambda represent? So lambda itself, it represents wavelength. So for this part, if you want to compare it to something, you can compare it to frequency. So for frequency, on the other hand, it's like 1 over t. But what is t? So t, no, it's not for time, it's period, okay? So 1 over t, the 1 here shows the 1 unit of time. So it's like, for example, 1 second, like within this amount of time, within like 1 second, how many periods were there? That's what 1 over t means, which means frequency. Similarly, for lambda, is the wavelength. So the 1, it represents 1 unit of the distance, where it can be 1 meter or so, or just 1 unit of distance. And within this 1 unit of distance, how many wavelengths are there? Now moving on to the next part, RH, what is that? That is the Rydberg's constant for hydrogen. So as you can see, the H below is for hydrogen. If it's helium or anything else like helium, it will be He instead of H, and if it's anything else, the bottom will change. And now moving on to the N1 and N2. So first, over here we have, so N, what does it mean? It is the principal quantum number. Okay, so the principal quantum number over here. And N1 and N2, what's the big deal? So for N1, you can choose like any number and all. Well, for this part, it's like you can choose 1, 2, 3, 4, all you want. But for N2, so it's like for N1, it can be anything like, for example, 1. But what about N2? So for N2, it's basically anything but 1 and cannot be less than 1. So it can be 2, 3, 4, continuing on. Well, N1 can be 2, N2 be 3, 4, and so on and so forth. And you can just continue writing and all, okay? So for this part, so it's like, you can have any number for N1, but N2 cannot be smaller or equals to it. Now moving on, we have the modern physics and the classical physics. So starting off with the classical physics, here we have F, which is obviously force, and then Q1, Q2, which is the charge of the proton or the electron, okay? And now moving on over here, what we have is that, so E is basically the charge. Well, since there's a proton and electron, one is negative, one is positive, right? So supposedly there is supposed to be a negative in front, but because the mv squared over r also has a negative in front, so they cancel out each other, and you can find r through that. And another of the classical formula is that the Newton's second law. So for the Newton's second law, what we have is that F equals to ma. So there's 3 laws obviously. So what is A is basically ma is equals to mv squared over r. Okay. So now over here for this part, what else do we have? So for this, as we know that for this part, but the thing about classical whole laws, we still have problems even after his from laws and all. So there are 3 listed here, although there's even more. So first, radius is so r being the distance over here. The radius. By using the classical law, you still do not know the radius. And by using the classical law, it does not explain why it emits light. It simply just has like a theory and all. So it's like it does not explain why light is emitted. And another thing is that although they made we still don't know like the number of photons, because for the photons, once we can assume that it's like each ray of light and all, it can be 1 photon each and all. But specifically, we do not know. And talking about photons, we also wonder like what about the brightness of the photons, and the luminosity and all those. Well, you still cannot figure it out through Coulomb's law and Newton's second law. And there's a lot more like acceleration of decaying and all those, okay? So for this part over here, despite the laws and all, we still cannot figure out a lot of things. So now that we have the Coulomb's law and the Newton's second law, which are from classical physics. Now moving on to the Bohr's assumption. So before that, despite the fact that in classical physics and all, we have some problems that we cannot decipher or solve. Even in modern physics, we still do not know how to solve some of the problems. And also the Coulomb's law, the reason why we can have this is because of the centripetal force. So now let's continue with the Bohr's assumption. So Bohr's assumption, quantization of angular momentum. So what is MVR? MVR, no, I don't mean by what M, V, and R are. So MVR together, they are basically the angular momentum. MV is momentum, while MVR is angular momentum. Okay? So for this part over here, it is L. Yeah. The symbol L is angular momentum. Now moving on, we have N, which we have explained before, which is the principal quantum number, and then we have the H versus line above. What is it? Well, as you can see over here, it is the reduced Planck's constant. Well, this is equals to, so what is reduced Planck's constant equals to? It is equals to the Planck's constant over 2 pi, whereas here you get NH over 2 pi. So that is the L, which is the angle, which is basically the angular momentum. So over here we also have V, the velocity over here, which we will have basically moving these 2 parts over here. Okay, well, we still do not exactly know we do not know what R is a radius and all this. Well, as you can see here, we have E, the charge, E squared, and then after that over this part where, as you can tell, that and R over here is E squared over 4 pi epsilon naught M times NH over 2 pi MR square. Okay, so as you can see for this part, this is basically the same thing as the V square. Okay, so for this part, what we have is that, so when we open this and all, this is what we get. And so yeah, you simplify the M over here and you left with 1 M above, and yeah. So now that we have gotten this, what else can we have? But wait, over here both sides have R, right? This R and this R squared. So why not just move this over here and move this over here, which will just get R instead. So R, which is is this. So R being epsilon naught n square h square over pi e square m. It is the Morse radius for hydrogen atom. So over here for this part, as you can see, this is what we get for the radius. Thus, we can get the velocity over here by subbing it in, and this is what we get. Okay. So just another thing to talk about is that about these problems about like emitting light and all, right? So emitting light is basically emission. So when there's emission and then there is absorption, right? So there's like the emission spectrum and the absorption spectrum. So the emission spectrum is like emit the line. So when you draw it out, it's like lines, while all the other parts are black. While it's like for absorption spectrum is the opposite way around. Well, let me just tell another thing is that for black is the absorption of light. Okay, there's no such thing as black light being emitted. There is no such thing as black light being emitted. So if you see black, it's just the absorption of the light. It's basically void of light. Okay. Well, on the other hand, we also have the both of them together, the continuous spectrum. So continuous spectrum is like the whole spectrum without any light absorbed. Okay. So for this part now, we continue with the next assumption here. Well, for this part, what we have is Einstein assumption, Planck-Einstein relation. So E being energy. So for this part, it's basically the difference in energy. Okay. Whereas we have the Planck's constant times nu, whereas it will be hc over lambda. So as you can see for c here, so c is basically the speed of light. Then 1 over lambda, well, you can just straight up just write from the, well, we have proven over here like already. So for this part, we can just straight up write that. It's basically like this, okay? So because as you can see 1 over lambda, Rydberg's empirical formula, and if you sub it in, yeah, you can just get this, okay? Alright, now over here for this part, we also have EM being mechanical energy here, which is potential energy and kinetic energy together. So as you can see for this part, for potential energy, basically half mv squared, and the v is subbed in. Well, for potential energy, we'll explain in future lessons. And so for this part over here, when you put them together, this is what you get as the mechanical energy. Okay, so as you can see, this is what you get, basically EM, whereas in this case is these two together. Okay, so for this part, the difference in the energy, as you can see here, you have this inside, whereas you have, so there's over hc, right? Means that at the denominator, instead of being h squared, it will be h cubed times c. Whereas obviously having the negative over here, this part will be negative and this will be positive. Well, as you can see for this part, because of like the difference over here, E2 minus E1, so the principal quantum number will also be different, which will have this n1 square and the n2 square as shown here. And basically these two put together, you can take this part out, okay? So when you take this part out, so for this, these two will also be switched, and then this is the Rydberg Ricks constant for hydrogen. So the Ricks constant for hydrogen is me to the power of 4 over 8 epsilon naught square h cube c. Okay. Alright, so for this part, that's what we'll mainly recap for today. Okay, for the Ricks empirical formula. Okay, so for the Ricks empirical formula, in case you want to know more, like for this part, the Bohr's assumption, right? So other than this, other than L being equals to these three, we can also have other options. So L being MVR, we can also have we can also use it for others. So for this part over here, you can either separate it by MV then R, or else V and R. So first of all, what is MV? MV is momentum, but instead of the angular momentum, it is linear momentum, which is PR. Well, on the other hand, VR, what is it? So what is V? So V is omega R, which is omega R square. Whereas over here, what we'll have is that M times R square is I omega. So over here for this part, the initial turns from M to I, which is the moment of initial. Okay. So for this part over here, we have F. So F, for the Newton's second law, F is equals to ma. But what? So ma is equals to what? So ma is equals to m delta v over delta t is equals to wait, give me a sec. So over here, when M and V together, so for this part, it is basically delta P over delta T. Okay, so this is also the Newton's second law for linear. So now we have M. Well, despite the fact that it is M, it is still the Newton's second law. It just that it is angular, like circular and all. Okay, so it will be F times R. Okay, FR. So FR, what is it equals to? F, so it is M A then times R, right? So over here we'll have M delta V over delta T R, which is equals to M V2 plus V1, minus, over delta T times R, which is equals to, so for this part over here, so V2, also V is omega R, right? So over here what we'll have is omega 2R minus omega 1R over delta T R. So over here you can put the r together, which is mr squared, then after that delta omega over delta t. So first of all, omega. So omega is the angular velocity, okay? So angular velocity over the t, it will become, so as you can see, first of all, the initial over here, m will become I, the moment of inertia, then times beta, as you can see here. So over here, if you compare it to in front, it is basically delta L over delta T. Okay, delta L over delta T. So for here, just so you know, both of these are the Newton's second law, despite how different they may look. It's just that the first one is the Newton's second law for linear, while this is for angular, whereas we'll have another R. So for Newton's second law for linear, what we get in the end is delta P over delta T. Well, for angular, you can either say it is I beta or delta L over delta T. And there's like other ways to write what L is, the angular momentum is, okay? So over here, that will be all for this lesson. Just take a quick look. And that will be all. Thank you for your watching.